Good afternoon, everyone, and thank you for attending our Planning Your High-Tech PCB Design for the Lowest Possible Cost webinar. My name is Danielle Correa, and I'm the Marketing Coordinator here at EPIC. Before we get started, I just want to let you know that you will be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel located in the webinar control panel, and we will try to get to all of them by the end of the presentation. If we don't have time to get through all of your questions, we will be sure to reply back to you by email. Also, we will be recording this webinar, and we will be posting both the recording and the slides on our website and on our YouTube channel. Our presenter today is Al Wright, our PCB Field Applications Engineer. Al has been in the industry for over 35 years and has been with EPIC for more than 16 years. As a PCB Field Applications Engineer, he handles a wide variety of responsibilities, which range from reviewing PCB designs for manufacturability during the quoting and design stage to interacting with off-site manufacturing facilities to solve technical issues during production. He has worked on more than 100,000 different PCB designs from his start way back in 1981. So without further ado, I will pass it over to Al.
Hello everybody, and welcome to Planning Your High-Tech PCB Design for the Lowest Possible Cost. This is a topic that comes up quite a bit. And here's, in a perfect world, a high-tech PCB design could incorporate every desirable feature and function, and cost would never enter the conversation. The real world is very different. Products are often designed to meet a price target or a development budget. This webinar will provide some guidelines for keeping your costs as low as possible while still meeting your critical performance requirements. So our agenda will be to describe how complexity adds cost, then showing that you want to decide which features are critical early in the project, learn to avoid needless complexity, and then we'll have some examples where we reduce the impact of specific cost-adding features of your board. At the end, we'll have something about material utilization, which is very important, and then the conclusion that I hope by the end of the webinar you'll realize you're not helpless as far as your costs go. So complexity adds cost. We all know that. Cost control is important for all types of PCBs, but as boards become more complex, they naturally cost more. It's the way of the world. State-of-the-art PCB designs often require more expensive materials and more complicated manufacturing techniques. So at the right, I have a little picture of how high-density interconnect boards, these are boards where you have to laminate them more than once, multi-layers that you have to laminate more than once, and how the costs increase quite a bit as you add different stages of HDI. So a normal board at 100%, you add one stage of HDI, you're looking at about 40%, then 80, then even 240. So it can get very expensive. Sometimes it's unavoidable. So speaking of unavoidable, your first step in controlling your costs is to identify what really is critical. And the point of this, and I want to stress this, it's not to discourage highly complex designs. We can do that. You need what you need, and some adders are going to be unavoidable as you climb up the technology ladder. If possible, though, you want to choose less costly approaches to both critical and non-critical aspects of your design for your maximum savings. And continuing with identifying what's critical, decide which costly features are truly essential for function, and then you can look for ways to try to reduce their cost impact. To do this, you need to first understand which items will always add cost. So some adders can't be avoided. High-frequency materials, for those of you designing RF boards and so forth, when they're required, those materials run from 7x the price of FR4 up to maybe 15x. They can get really, really pricey. But if you need them, you need them. State-of-the-art components, particularly dense BGAs and big BGAs, require high-density circuitry, plus costly sequential lamination and laser via formation. Now this board down here happens to use, if you can follow my arrow, it looks like a 4-layer board with all high frequency material in there. So that was a pretty expensive little board to build, even though it was very small. Again, continuing with some adders can't be avoided. Things like multiple surface finishes or edge plating complicate the processing, add material costs and so forth, a little extra time. Heavier copper weights also require more time and materials, mostly plating time, but there are other costs involved there too. Now here is one example of reducing an unavoidable cost adder. Here's an adder you have to have for performance, but we're going to look for a cheaper way to do it. And there will be other examples later, but we're kind of skipping ahead with this first one as an example. When you must use expensive options, sometimes you can limit their impact. So for example, the cost adder at the right is the 8-ounce internal copper, which you can see here. It's a 4-layer board with 8-ounce internal copper. Fairly costly material to buy. What you can do in a case like this, consider reducing the copper weight and utilizing redundant plain layers of lighter copper instead. And the added layers will reduce plating time, plus handling, plus material costs. So even though you're going to what would seem to be a more complex board, by going to 4-ounce copper, you're buying a copper weight that is available as sheet stock. You don't have to go through a plating process. Your imaging process is simplified. Everything's simplified. You're going to end up saving a little money there. The next big point is to learn to identify what is avoidable. And today there are many people designing boards, from hobbyists to students to professionals. When I started, it was all professionals really. Now everybody can get in on the fun, and you need to just kind of understand what you're doing when you're looking at cost control. So designers who work on board layouts every day usually understand when they're pushing into difficult or costly territory. They'll usually pick up the phone or look around the web or whatever to find a cheaper way to do it, or to find out what kind of territory they are wandering into. Others, though, with less experience might decide on a feature for its apparent utility without really grasping the cost impact on the bare board, and they end up getting sticker shocked when they try to get some parts made. So the first step is to learn what is normal. It's important for less experienced designers to gather as much knowledge as possible. This will enable them to get a feel for standard layout and manufacturing guidelines. And some of the source include books, internet searches, and discussions with experienced professionals. And to plug our own company, Epic's blog is a good resource, which includes many relevant posts on PC boards and on some of our other products as well. I think I heard a figure like we had 700 pages of content on these topics. So there's a lot of stuff there, and you can help yourself to it. So now we're going to get into some adders and find out how we can save a little bit of money against the worst case. High-speed, low-loss materials are very costly, materials like Rogers, Taconic, etc., but they're often necessary to meet critical signal requirements, like an antenna or so forth. These materials usually have to be special ordered, and minimum quantity pricing can also kick in, and that'll add further to the price. You want to consider using FR4 at non-critical layers to save cost. This is if you have a multi-layer. If you have a double-sided board, you're kind of stuck, but with multi-layers, the cost can really add up. So in our 6-layer example here at the top, we're using Rogers materials at all 3 of these core positions here. And the cost, let's just say, as a round number, is 10 times the cost of FR4. But you notice that the only critical signal layers are between 1 and 2. 1 is the critical signal, 2 is the ground. Everything else is really just taking up space. So why are you really paying 30 times what you would normally pay for FR4? So you might want to consider, if you're down here, use the Rogers at the critical position, and then insert FR4 at the other 2 positions. So you've now gone from 10x, 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 which is 30x, to 10x, 1x, 1x, which is 12x. And that is quite a savings. So That's something you can do with certain Rogers materials, and I can probably go into that more afterward. Another adder is high density interconnect with blind drilling and sequential lamination. Some boards get to be so dense and some components get to be so small that you need to do drilling that does not go all the way through the board. And if it doesn't go all the way through the board, and you have to drill it in stages before the board has been completely laminated together. So HDI processing like that adds many steps. There's often no way around it for tight designs, especially stuff with BGAs, because BGAs just crowd everything else out. So you want to be sure when you're using HDI processing that it's actually necessary. If your board's not dense, you can usually eliminate some or all of the extra drilling and lamination. And this board right here is a fairly simple board, which incredibly, at 4 layers, required 4 different stages of drilling when we first got it. And I had to kind of take it apart and help the guy simplify it. Another adder is via and pad and Castellation. Via and pad processing and Castellation meaning edge-plated holes. These require careful handling and significant extra processing. One way you could save on via and pad is that if you don't need to recover your drilled pads for soldering, just consider using just an epoxy plug from the opposite side of the pad to prevent the solder from migrating through the hole when you assemble your board, and you'll save a good deal of money over trying to cap plate all those pads if you don't really need them cap plated. High density boards are kind of a cost adder all by themselves. High density circuitry is a challenge. Below about 4 and 4, which I guess is 0.01 millimeters, many things can go wrong in production. Tight geometries are achievable, but they cost more because there's a greater likelihood of some level of scrap. You're operating closer to the limits of your process, so you end up throwing stuff away, and you end up having to be very careful during the process. So depending on what's driving the density, one thing you can consider doing is to reduce the density, again, by adding layers like we did with the heavy copper earlier. If you add layers, you have a little more room to work. That isn't necessarily going to work with a BGA if it's a big BGA, but it will work with some high density situations. Here's an adder. We see a lot of jobs like this where you need the FR4 cores to be delivered with unlike copper foil, like 1 ounce over 2 ounce or ½ ounce over 1 ounce or something like that. So a variety of FR4 multi-layer cores are usually available in inventory with a fabricator. Sometimes, though, they must be special ordered, and it usually happens when you have these different ounce weights on the 2 sides of the core. And our suggestion for reducing cost is to try to use plain layers with the same copper weight as the signal layers. These cores will be in stock, they'll be available at standard cost, and they'll be available for immediate use. So you'll save money, and if you need a quick turn, you're going to get your boards more quickly. So the example, we have a 6-layer where we have 2 ounce grounds, ½ ounce signals. That might be a little bit of an exaggeration in most cases, but I'm trying to illustrate a point. So one option would be to use 1 ounce on both sides of the core, if you can get away with it, or to even use ½ ounce on both sides of the core if you can't. A lot of this is driven by how fine the signal layers are. If you have very, very fine pitch trace and space, you have to go with the lightest copper you can, and then try to match it on your grounds. All right, I'm going to dwell on this relatively low-tech aspect right now, the importance of material utilization, because this is really overlooked. Good material utilization is often the most important factor affecting the cost of your PCB. A fraction of an inch increase in your outline dimension could force your fabricator to run fewer parts per sheet. Programs like QuickFit can be useful for estimating panel usage, and what we have here is a screenshot of QuickFit where I've plugged in some parameters the panel size being this, the part size being the dark gray areas. The number up is 9, spacing between the matrix and how much of a border you need. Generally want to use about 1-inch border. And the usage on this is 75%, which doesn't sound that great, but it actually is very good. You can see everything's very snug. There's not a lot of wasted space at either edge. So that's what you're looking for. You're looking for a process sheet that ends up looking like that once you place your boards on it. And wanted to make the point, a poor fit is a gift that just keeps giving. And it costs you money at every stage. A 7.95 by 10.95 outline is going to fit 4 up on an 18 by 24 sheet, while another one that measures just 8.1 by 11.1 may only fit 2 up. And sometimes this can be mitigated by the use of smaller sheet stock, but in many cases the sheet has to stay the same. Either way, you're kind of paying for what gets cut off anyway. And the reason a lot of times you can't really shear down the material to a different size is that a lot of fabricators, particularly in the States, only have 1 or 2 sets of multi-layer press plates. So they're pretty much locked into, say, an 18 by 24 panel or a 12 by 18 panel. So if you have this 8.1 by 11.1 over here, really all they can do is tip them on their sides like that, butt them up against each other for 2 up, and you're wasting an awful lot of material here around the edges. So bear that in mind. If you have control over your board size, exercise control over your board size. Why is it so critical? Running fewer boards per panel increases the cost of materials and the time spent handling your board at every production stage. So particularly with the high frequency or exotic materials that we saw before, where you're like 7x to 15x the cost of FR4, you're going to see your material costs just skyrocket right out of sight. And again, the panel on the left is basically, this is the same panel from the last slide tipped on its side. You're getting this many boards that you have to process and handle, or you're getting this many boards that you're going to have to process and handle. So even though a lot of the numbers come out relatively similar, you're still wasting time, and you're probably wasting a lot of materials too. And this kind of breaks down the bad utilization. Some places where it hurts you. At imaging, it wastes film because the film tends to come on rolls in fixed sizes. So why put film all over the part of the panel you're not using? Drilling and routing, you're not really increasing the drilling or routing, the amount of drilling and routing you're doing. Well, routing you actually are kind of spending a little more time, but drilling and routing, you're loading and unloading the table between cycles. Plating is increased handling. It's wasted metal around those unused parts of the panel, and it's reducing the fabricator's tank throughput. So you're going to get charged for that. It's time. And heavy copper, again, same issues as plating. It's just kind of magnified when you have heavy copper. If you're putting more than about an ounce of copper on, you're paying for more time, you're paying for more copper. And it also affects imaging with heavy copper because you have to do different things in the imaging department to set up your circuit so that the plating goes smoothly. So you do cost yourself at a couple of stages there. So my suggestion is that at the project planning stage, try to choose an efficient board size. If you have a contract manufacturer or an assembler, find out what their panel preferences are, and if you can design your board to match their panel size, their assembly panel size, everybody's going to be happy, and you'll save some money. EPIC's material utilization document here at the right lists some good yielding sizes, and it explains how fabricators use some of the space. And you can use this as a reference, and I have this available if anybody is interested in seeing it. But it basically goes through on an 18 by 24 panel. Here are some good board sizes. On the left, here's how many boards it yields per process panel. And there's one matrix for multi-layer boards, which are 3 layers or more. They actually require a little more waste area around the edge of the panel. And the other one is for 1 or 2 layers, where it could be a little more aggressive around the edge of the panel and use slightly bigger board sizes, about an 1/8 inch bigger in both directions before you start getting into trouble. So the takeaway of all this is that high-end features add to the cost of your board, but you still have some control. In a lot of situations you can save yourself some money by thinking it through, talking it through. You need to learn to prioritize what you really need over what might be nice to have. If you don't need every bell and whistle, cut some of them out. You'll save some money. And try to find less costly ways to achieve your design requirements without breaking the bank at every turn. Again, save a buck where you can, whether it's a high-end feature that you really desperately need, or if it's a low-end feature that's just kind of costing you money off to the side and you don't even realize it. Try to look for those opportunities to save. And the last thing is very important, ask questions. You can always ask your fabricator, and there's a lot of other sources as well. So with that, I'll kick us over to our product page and put Danielle back on.
Very good. Thank you, Al. Well, Al reviews the questions that came in. He's going to answer those in just a bit. I wanted to briefly mention some of the additional PCB-based products we offer here at EPIC, including custom battery packs, flex and rigid flex PCBs, high reliability user interfaces, cable assemblies, RF products, and our energy efficient fans and motors. All right, next slide, please. Al?
Okay. Yep.
All right, and I'll turn that back over to Al, and he'll go over some of the questions that came in.
Okay, here's one. Okay, under high-speed materials, you show how to make hybrid laminations of high-frequency materials with FR4 to save cost. I've always been taught not to mix different materials in a stack-up. How reliable is one of these hybrid laminations? Actually, they're quite reliable. The thing that you have to avoid doing is using some of the stranger high-frequency materials, the ones that are made out of PTFE, Teflon. Those don't always play very well with FR4. But, for example, the Rogers 4000 is a hydrocarbon ceramic, and the CTE is close to the CTE of copper. The holes don't require special prep before plating the way Teflon does. And the Rogers 3000 series is a ceramic-filled PTFE, which is also okay with FR4. So you really want to study the material manufacturer's application sheets and find out which materials are compatible with FR4. And as I said, you can save a bundle of money by using the right combinations. I'm considering using blind drilling for an upcoming project. On the HDI blind drilling slide, how would the designer have realized he did not need as much blind drilling? Well, if you don't mind, it'd be better if I illustrate this by looking at this one. One of the clues is if you don't see a lot of density, if you don't see a lot of copper density on your layer, you probably don't need to be using a lot of blind drilling. You don't have any really fine pitched components on here, and you don't have a lot of circuitry that would interfere with placement of regular through-hole vias, so why not use that space? This particular board had an antenna running up the right side here. You can just see it, and it comes out of here. I thought at first that they were using blind drilling to prevent stub effect from causing a problem with the signal from the antenna, but it turned out that wasn't the case. They were just using blind drilling. So I came up with a whole bunch of different little locations where we could add vias, off to the side. Like this via here is not really in the pad. This one here is in the pad. It doesn't need to be in the pad. You can run a trace out here, drop a via, make sure that it's not hitting anything on the internal layers, and come out the back side. So that's what you want to look for. If you don't have density, you really probably don't need high density blind drilling and so forth. And well, let's see. Why would somebody require Castellation on a board? And what makes it difficult? Aren't you just cutting a hole in half? Well, yeah, Castellation does seem simple, but it's not really as simple as cutting a hole in half, because what happens is you have, let me see if I can find that slide. Yeah, right here is a Castellation, an example of a Castellation. It's basically an edge-plated hole that's been cut in half. What happens is you have to primary route this so that you'll be able to plate that sidewall of the board. When you primary route it, when you get to right here, the first part of the hole wall that you hit, there's copper plating in that hole wall. And the router has a tendency to push it back into the hole as it goes by. So on this board, you'd have 3 opportunities where you might pull the copper free and push it into the hole. Once it's in there, it's a bear to get out. So you really need to know what you're doing with processing, and you do need to kind of keep an eye on this when you're doing it. And the reasons people use it is sometimes you might want to take a little board like this and piggyback it onto a larger board or a very simple board underneath. So you get the extra features that are on this small board, and they're actually connecting in at these Castellations to the other board. You might have surface mount pads where each of the Castellations is. You put this board down against those surface mount pads, and then you solder using these castellated holes. You solder to the surface mount. Now you have a little board with extra function piggybacked onto the top of your main board. That's largely what it's about. There are also a handful of connectors that connect into those too, but a lot of times it is for like a little daughter board. If you're interested, there's a Spark Fund page that shows how to solder those. That's kind of interesting. What's the next one here? Why don't board shops keep specialized cores in their inventory so they don't need to be special ordered? Well, that would be good, but there are so many possible variations of thickness, type, and foil thicknesses that material might sit around in inventory for a long time, and it just shows as unused inventory, and nobody really likes to run that way. Everybody's trying to run as lean as they can, so they carry a good stock of the stuff that they use all the time, and then if they have a need for something else, they do need to special order it. And again, that included things like the high frequency materials and the cores with, say, 1 ounce over 2 ounce copper. Those are classic examples of things that generally aren't in stock. Do this one. I think we're running a little bit long here, but let me see about this one. Oh, yeah, this is actually a good one to finish with, I guess. My board needs to be a certain size to fit into an existing enclosure, so I can't change the size to improve the material utilization. Why don't fabricators just trim the raw material to fit each board size better? And then at the end it says, can I get a copy of the utilization document for future projects? So let's go to the trimming thing. And I kind of touched upon this a little bit with multi-layers. A lot of fabricators just have a couple of sizes of multi-layer plates. So they're pretty much hemmed into using raw materials that fit those multi-layer plates. And that's one reason. The other thing too is, even if your fabricator is trimming the material to fit your weird board size, you're probably paying for it anyway. They might not be telling you that. They might be trimming it so they're not wasting plating and so forth throughout the production line, but you're probably paying for it anyway. My old company, we had a customer who used some weird board size, like 11.8 by 8.8, that just didn't fit well on existing materials, and I think we ran those on 16 by 21s or something, and we were cutting off a strip of 6 inches of material all across the panel before we cut the sheets out for that job every time. And they had a whole bunch of part numbers. For some reason, they had decided on that as their standard panel size, and it was just costing them money all the time, but there wasn't much they could do about it. All their lines were set up that way. So, again, sometimes you can't change your board size. Sometimes you're stuck with what you're stuck with because it has to fit into an enclosure or a rack rail or something. But when you have the opportunity, you can look at something like that matrix and you can try to fit your board accordingly. And again, involve your contract manufacturer, because they might need rails along the edge of the board to hold things through conveyorized equipment. So your board size might look good, but when they put it on their panel, it might blow the material utilization. So there's a lot to think about, but there's a lot of money to be saved as well. So I've actually skipped ahead quite a bit here, so I'm going to go back to the product page here and then Q&A, and then thank you everybody for attending the webinar. And if there are probably a couple more questions, and I will get to those as quickly as I can. Thanks.